Hello and welcome to follow my videos. My name is Matti Ylitalo and today our focus is balls cooling in oil bath. Just a second, I'll put the presentation mode on. Typically we have a vessel filled with oil and we have hot particles. Typical particle diameter is maximum some millimeters. In this video we will first look at what is the physical problem, and then we will create a Python code to calculate the ball temperature during cooling, and we will calculate an example. So now we have steel balls in oil, and we can assume that our vessel is well insulated, so no heat is escaping to environment. So what is happening is that our hot balls are cooling down and this oil is warming up. So we can write that the ball temperature is changing because this convective heat transfer from those balls to oil, and the oil is warming up because of that heat transfer. And this is our equation what we need to solve now. Our task is now to create a model to solve the ball temperature. We will use Python code. If our balls are small enough, we can assume that the temperature inside those balls is uniform. This is true when our Biot number is small enough. Biot number is a function of heat transfer coefficient times characteristic length divided by heat conductivity. If this Biot number is less than 0.1, we can be sure that this assumption is okay. And for millimeter scale balls, this Biot number is typically very small. So this is okay. We are now creating simplified model. So we can now assume that our oil temperature is uniform, and we can assume also that our oil is not moving, and as we have already discussed, we will neglect heat transfer from our vessel to environment, and we assume that our balls have no internal gradients, and we also neglect radiation. We will later discuss what is the effect of radiation in these kind of cases. We need to add some checks to our code. We will calculate how much energy is removed from our balls and how much energy is gained by our oil, and then we will also calculate the convective heat transfer from our balls. Here we have an example. I asked this Python code from ChatGPT, and I calculated an example case. And in this case the ball diameter was 1 centimeter and the ball initial temperature was 1000 kelvins and oil initial temperature was 300 kelvins. And the total mass of balls was 200 kilograms and the mass of oil was 500 kilograms. And I assumed this convective heat transfer coefficient to be 40 watts per square meter kelvins. And here we see the result, and we can see that if the initial temperature is 1000 kelvins, it takes around 280 seconds to reach the 500 kelvins, and to reach the final temperature it takes around 900 seconds, and the final temperature of the ball is the same as the temperature of the oil, and it seems that it's around 370 kelvins. And in this calculation I use this integration time step 0.5 seconds, and it seems that if we check this energy balance we have a small error in that. But then I tested the same case calculating with a small time step, and now this error is 0. So when calculating with a small time step we will get rid of this error, but the cost is longer calculation time. In my laptop it was around 20 seconds, so not so bad. In this kind of a simulation the biggest point is this estimated heat transfer coefficient. But one way to develop this kind of simulation is that if we can measure the oil temperature during cooling process, from that data we can calculate what was the real value of this heat transfer coefficient. You can also work with heat transfer coefficient calculation. When the oil is warming up you will have natural convection, but if you have a fan rotating this oil you will be working with forced convection. In some cases you may be also interested in ball internal temperatures. Then you need to solve this ball temperature equation. What is the role of radiation in this kind of simulations? Typically when we are working with oils and we have moderate temperatures, we can leave out the radiation from our calculations. That's because liquid absorbs infrared radiation. But in some cases, when the temperature of those balls is very high, the oil will vaporize around those balls, and that creates a layer of gas around those balls. And in those cases the effect of radiation can be very high. And in this example the heat transfer by radiation is at the same level as the heat transfer by convective heat transfer. And we can say that at the beginning of this cooling process the effect of radiation can be very remarkable. I added this radiation calculation to this Python code, and I calculated the same case, and it seems that this cooling is now much faster. But we need to remember that this cooling is dependent on ball emissivity. If the ball emissivity is 0.8, this effect of radiation is quite remarkable. But if the emissivity of those balls is only 0.1, so the effect of radiation is quite small. As a summary, I would like to say that when you need to calculate this kind of cases, this lumped capacitance model is often good enough. And you need to know those balls and oils, material properties. And when calculating, use always a small enough time step in your calculation. Check this energy balance and check this Biot number. Okay, that was all this time. Thank you for watching and see you. Bye bye.